to show a little what we are doing. And certainly I must apologize if some things will come again, as we heard some of them. And some are related, perhaps some are also different perspectives. And first, I would like to mention that most of the work which I will present have been done by my younger colleagues. So Simon Chopat, Tine Porenta, Micha Ravnik, and David Sech have contributed to different parts, and without that, wouldn't be this presentation. And the other thing which I should mention is that part of this is also coming from the stimulation and exchange and collaboration with our experimental group led by Professor Mušević. And so this is a kind of setup. And now what I would like to tell is a little in this is here my outline. So definitely we are talking here, try to say that we are talking about topological soft matter. So a matter where these topological aspects are becoming very important, how this matter responds to perhaps external stimuli. And now what is behind is that we have, in case that we have colloidal system, very important are things which are interactions between different particles which are seen and which we have seen already in previous talks. And then we tried a kind of phenomenological description which was used also in the previous cases, and so I will be very brief. And then clue to the many of structures was again this entanglement between these clinician lines, and here we will be particularly interested what are the reasons which can stabilize different kind of structures. And so the interplay between this geometry and topology, then description between formal ways how to define some of these loops which we see and what can be, how they can combine together. Then forming like two-dimensional network where we have seen some pictures already. And then a step toward three-dimensional declination network where also one can use the same picture how to predict the structures in this three-dimensional opal type structure. And then at the end, or the last part will be devoted to the knots which are inside a confined area of a cholesteric drop. So if we go first to this motivation, this I can skip because some of all these pictures practically you have seen in the previous talk. And so I can just go further and say a little more about the part which will be colloidal. First colloidal part devoted to a rather thin layer of colloidal particles which are tightly confined between two plates where you have strong anchoring on one side. And this anchoring can be such that in both directions, up and down is the same direction, or could be such that enforce some twist. This twist can come also from intrinsic property of the liquid crystal or is simply enforced. And then we will talk mostly on this so-called homeotropic anchoring, normal anchoring to surfaces on these colloidal particles, while on the surfaces here was a strong planar anchoring. And so this is a kind of a region where our colloidal particles are confined. And so to say a little what is our background is similar as it was in the Junich's talk. So it's in fact the free energy which has standard phase terms, and we have derivative terms where we add this also chiral term because we will have cholesterics which must be described. And then we have a coupling towards surfaces, either on colloidal particle or on surfaces. And then the idea is then to look for the minimal free energy states, but certainly not only minimal, but some which are local minima, which will be interesting. Now, procedures are simple. kind of a relaxation, finite difference relaxation method, and limited by our computer power which we have. But it's important to recover defects in such a way that the resolution of our mesh must be such that it comes in the range of the nematic correlation length, otherwise things cannot be good. Now, how our boundaries, this really depends on the particular case. Now, important thing here is also visualization. We heard a little about different techniques, and it was mostly oriented towards Pontryaghin's approach, which certainly adds more possibilities, but we use also some other things which expose the structures, and some of them are. If we have the defect line, so director lines, we are usually plotting isosurfaces of the order parameter. For instance, if there is a -1/2 line, we have a kind of line tube where you have constant order parameter a little lower than the bulk value. But in fact, this is a kind of better would be here to plot a kind of threefold ribbon. Also, sometimes this complicates the view, so it's sometimes better to go to a simple presentation. But this threefold ribbon here already tells more about the local director field around.
So, I'm sorry, I don't understand what you're plotting in the threefold ribbon.
Sorry?
I don't understand what you're plotting in the threefold ribbon.
In the threefold ribbon is in fact the shape is adapted to the local director field. So that means it's a more schematic. This one, at least here, is a schematic type, which gives you the symmetry of this director field here around. So if one would like to have to go into a little more detail, I can show in the next where one can get this ribbon exactly. Now, for instance, this other presentation, which tells you a little about splay band deformation. And we know here we have band deformation, here we have splay deformation in these areas. And now if we plot the areas of large splay deformation, you get this, let's say, this kind of threefold ribbon already. Or if we pay, the same is with the band. So one can use one of them to get automatically also features which are just giving you the shape of threefold ribbon.
So the thing you're plotting.
The central part here is in fact the area where it's really ordered melted down. Yeah?
I think he wants to know what the color coding is.
Yeah, color coding here is unfortunately it's mixed around. So here this is an old picture, while this here we use the blue or the yellow for the ribbon, while here its color is sorry.
The question is what's the quantity, but I think the answer is given up there. It's this particular second derivative of the nematic order.
Yeah, this is the formal way how you really can calculate from your texture which you have.
And the first thing you're just plotting the magnitude of the scalar magnitude of the order parameter.
See, here it's this small difference, like 10% in this case, gives you such a tube of this. You can plot more or less depending whatever you want.
So in one case you're plotting the magnitude of the order parameter, in another case you're plotting a particular derivative.
Yeah, and here is also, it's true that this was all this area, this is bigger than 0.02%, or here is -2%. So therefore here is just a simply cross-section, is a flat area, yeah? And similar thing, one can plot also the deformations in a twist. What is here plotted? This is another possibility that we somehow deviations from the natural twist. If there is a natural twist present, and we look for deformations up and down from the natural twist. That's the other possibility, which gives you some other details of the structures which we will have as well. So that's another possible view. Now going to these two particles, where we have colloidal particles, if they are such that, if situation is such that this so-called bipolar structure is and local minima in energy, then they organize in such a way when they are close, they attract each other. If they are in the state, if you are in the state that you have a Saturn ring, then they are different arrangement. And see, these all have a resemblance to electrical dipoles and quadrupoles, but one shouldn't take these details, particularly in near fields, are so different that one must really calculate the interaction in detail. And what was mentioned by Garrett before, that a few years back we find out also these entangled structures which are substantially different from this other cases when you have separated no sharing of the disclination line. Here you have sharing, and this sharing means that the interaction when you try to pull particles apart is different, so it's more string type. Now, what is important if we go back to this ribbon? That in fact, if you have a loop, we have these closed loops, it's important that things match together along the loop. This cross-section, if you go around, must come together if you want to have a kind of loop. So that means very important is what happens to this cross-section along the loop. And therefore here distinguish two possibilities. What can happen is, one is that the ribbon is simply twisted, or it makes a kind of 3D right type so it has a right. So that means these two deformations are present. One can calculate them for each particular solution already, so it's something what could be calculated from, or you can, from a model structure, you can also directly get this integrals, which tells you what are these numbers. But it's important that these two numbers are entering into so-called self-linking number. So that means this is a kind of important invariant of our loops. And if we take here two examples, on an example of a very simple loop, we have here both are zero. It's a flat Saturn ring. But now there is more. One can put all this together and relate to the charge, but unfortunately relation is such that it gives you just only limitations on your charge, so that you conserve the parity, but not much more. So the sum of all self-linking numbers and sum of linking numbers together plus number of loops will give you charge in the modulus of 2. So that means these are the frames, how these things can work and what they can. But if we have situations like colloidal particles, we know that these particles in the homogeneous nematic, totally there is no long-range deformation, all is localized, and if we associate with each particle certain charge, then we must say, okay, the rest must compensate this. And how this goes, then one can in fact check how this, if you calculate self-linking and linking numbers also from numerical results, then you must fit this within this modular 2. That's all what you can do. And here, definitely one should mention that there are more on these things, that this self-linking number was here previously calculated on the base that this cross-section is constant. But that is not in general true. It is reasonably well, it works reasonably well for colloidal systems. But if you go like in blue phases, there one can see that things can be, particularly if they are affected by external fields, particularly, that things can be very different. So that means that the cross-section could substantially change. If this is true, then in this case one must, instead of self-linking number, use something what it takes also into account that during going along the loop, you also must transform your cross-section. But that's now beyond what we can do today. Now if we go to this particular description of this, what we have seen, these knots, we must a little understand how these knots could be put together by really what they do. So, but this is done on this simple dimer structure where one can really see how this can work. So if we have a structure of a dimer with two separated Saturn rings, one here, one here, they are both deformed if the particles are close together, and so that means, but there are areas where disclinations come close. And what is here important that here these areas are such that disclination lines comes practically perpendicular one to another. And then there are cases also for other structures which observe so-called figure of theta, where you have two rings, and here again is this area where you have crossed disclination lines, but on the structure which is made of two loops which are orthogonal to each other. And here is this figure of 8 which I showed before, where again have areas where we have this orthogonal crossing. And this figure of omega is another one which is also a reasonably stable structure. And in all these cases we see these areas where things could be restructured to easily go from one structure to another. And this area of this is a kind of tetrahedron where you have two segments of our disclination line which are orthogonal to each other, and field inside is very homogeneous in between two lines. And that means the line which comes in has this threefold symmetry, and all this is in fact all these are ribbons. And here on each end such a line enters or goes out. And so if you would think that you can restructure this tetrahedron simply by rotating it in different directions around different axes, you mean that you can go between different structures which we have here by simply affecting only a very small area. And this can be done if you have a laser tweezer which is reasonably focused, so it should have just the right direction of the field here. So field should be in this appropriate angle, and then it's easy that things really restructure. Now, what they do in usual experiments, they just hit everything and wait, and something happens. So, but if you would have also this combination with more precise tweezers, you can do a directed switch turning around. Now, using this previous scheme of counting self-linking number on the right, one can do this for all these simple cases. This was 0, as I mentioned before, while here we have 2/3 for both cases which have this continuous loop. Now, what is perhaps interesting further and should be mentioned is that if you have this state of when they are close together, linked by a single line, but when you stretch this by, let's say they do this by laser tweezers, you can see if you follow our modeling that right is very close to this -2/3, which we have, I mentioned before. But when you stretch, then things deviate. What happens now here that right is changing, but then twist must change as well. Here we didn't plot twist, but both the sum of them are staying constant. So that means it simply is a balance of these two. Now the question is about this restructuring to go toward these knotted cases which were mentioned by Garrett. So if you have, this was our planar cell where things were done for this dimer. But the next step is that we have so-called pi cell. So that means the director goes from one side to another, no, pi 1/2. So 90 degrees cell, so 90 degrees turn. So that means in this case, one can have a kind of regular arrangement of colloidal particles where the disclination lines in between run in orthogonal way. Like this from top view is like that there are spots where this can come one to the other. If the cell is pi twisted, then there are even more possibilities. And what it means, and this one was the base for the making of these knotted structures. How it works and how, so that means restructuring here. And perhaps here in this other picture, I illustrate this, that such a restructuring, which can happen here in this kind of crossings, these are examples for the pi cell, can happen in some cases spontaneously in our modeling, or it must be forced by some additional external field or added. Now, so it's here shown that this one doesn't change. But if you stay stable, doesn't. But if you take this or this case, you follow the simulation and you will see that restructure. During this restructuring, lines come close, and then the particular twist deformation becomes large, and this simply goes from one to another. Certainly, we cannot claim that our modeling is the real state, because we have a very simple free energy or relaxation type behind only. Now to this knotted situation. In this knotted situation, when we have this lattice, for instance, here are 4 by 3 particles, and then there are areas in between where are reknotted, rewired here, and these are such orthogonal crossings. And these orthogonal crossings, again, the same picture as I mentioned before, can work on different spots. Now, you can apply this kind of rewiring on certain spots, and you get all kind of knots, which Garrett was also before mentioning. And now one can go for formal cases which were observed and make this counting of the number of loops, self-linking number, linking number, all this can be done. And it looks that works reasonable together with our numerical modeling. So here is another illustration which have this 3 by 4, but then arranged in a scheme which tells you how many of particular kind of knots can be formed within this case. And then there is this formal way how you use notation for knots, and then they are depending on self-linking number arranged, and here is a number of loops. So that's something what was done for this particular case. But now the question is to go to these 3 dimensions. So in 3-dimensional case, the question is if one can do something as well. So here we used similar approaches, but we were simulated by some rather more than 10 years back experiments from Clark's group, where they used opal structure permeated by the nematic liquid crystal. And that means nematic liquid crystal is filling all these voids in between, but these particles are in the face-centered cubic cell attaching each other, so it's not such a situation as previous colloidal system where things were flexible. This is still already is a solid, but with this void, then I think everything was coated for the normal anchoring on the particles. And now the question is how we can construct our disclination network inside. So then comes this idea that perhaps one can separate these areas of spaces in between into 2 kinds. That one kind are known our tetrahedron, which have seen before. The other are these cubic kind of voids where it has 8 vertices, while tetrahedron has 4. So that means decomposing the whole structure into the whole arrangement into such cubic voids and tetrahedral voids, and by seeing what can disclinations do inside particular voids, and then say, okay, everything is then connected when the voids are touching each other, and that you get the whole disclination network out of this. So that means that here one can count how many in the cubic voids. There are 7 possible states how the disclination lines can run. And all these are the same type of -1/2 disclination lines. So there are only 7. But if you want how they can be rotated in space, you have 45 possibilities how to arrange. And there is one which is a little different from the rest, whereas all disclination lines, one have here also a point defect inside. It's just one. And then we have these three voids, which are tetrahedral, and they have three states. And these three states, together with this situation, will give you a complete situation, because here I have shown this, that here voids, the tetrahedra here in between, and the disclination line runs from the tetrahedra toward the cubic void and further on. So all is in this way connected. So that means that you can really construct a total topologically correct ansatz for the disclination lines, just simply choosing these possible situations. Now, what then can be done? One can choose certain, and then you run the numerical simulation, which just then adapts also energetically the situation, and then you get in this way structures which are there, and you can also check how much the free energy depends, so the elastic contributions. But it's true that here is a tremendous amount of possibilities how this can be arranged. Now, for instance, if you have just a cubic cell, a unit cell of our face-centric cubic have 4 cubic voids and 8 tetrahedral voids. And then each of them have, as we have in 45, and one has 3, but then on power, so you have 10 to 14 states already in this small unit. So that means one can only play a kind of statistical game to see what kind of distribution of discrimination lines you will get. Do you get loops, how many, and what kind of knots you can think about, and so on. But we didn't play further with this. The question is if one can use this as a kind of memory. This I don't know. So this is this, and how much time I still have? What? 5 only, okay. So the next is then the cholesteric droplet. So as I said, why we studied cholesteric droplet? The reason is that we were here in the previous case of colloidal particles, we have these particles which were arresting the network. And network was stabilized by particles, and and all these knots and links and everything was happening around particles. Idea was here, these things can happen also inside, in the cholesteric drop, but not just on surface, but somehow in the bulk of which is confined in a drop. And here, what is playing here in the colloidal particles, the main thing were geometry, which was crucial, and anchoring on particles. Twist was just helping a little, that things were managing easier, more possibilities, and so on, but was not so crucial. While here, in this case, we expect higher chirality would dominate the things, while the confinement will lead then to kind of frustration of our ordering in a drop. Drops are very known things. And also in cholesterics, we have seen in the Maurice talk that about this Bouligand's work 40 years ago, when they were shown some links in cholesterics. But later on, I haven't seen any literature on this, that experiments were existing. So this was one of simulation. Then the other thing, that cholesteric droplets were becoming recently interesting also for 3-dimensional micro laser, which is an optical application. Now in droplets, so if we start with planar anchoring, these things are known. You have so-called, this Frank Price model is known for many years of cholesteric drop with the one line, radial defect line, but if you do a little more with the apparatus which we have now, you see that this is not a simple line, but it is a kind of winding of 2 lambda plus lines which produce this radial defect here. And there is nothing singular here. It's only on the surface you have a little singular. And then you have a substantial amount of splay and bend, which is happening here. And so details are clear. The same is a similar story is with the other, the diametrical line, which is less known and somehow is was studied therefore less because it's energetically less. Doesn't happen often. So and this one is instead of a plus line, which is in original model, you have a kind of sequence of ring defects, which some are singular, some are non-singular, and they are alternating. And in the center, you have a structure which looks like this toron here, just something very similar. And now the question is, the planar anchoring, is that something what can lead to any knots? We believe not, because we have these disclination lines which go to surface. As soon as this happens, then you can unwind all kind of complex structure decaying to simple structures. So therefore, it's much less frustration, much less of constraint. So that means this is not a candidate for looking for knots. But if you go to homeotropic droplet, what means now homeotropic? So that means that we have everywhere perpendicular anchoring on the internal side. And the simple structures which occur, for instance, here was pitch comparable to the radius. You get something what is a simple loop or three different loops, and they can be in this case even nicely organized, so that means the structure has lower energy with this one compared to this. And this is something coming out from quench studies, so was no here direction, nothing, numerical quench. Now if you go to a little more, so that we have this n was defined in this way, how many times the director turns, how many pi turns you have along the diameter. So here you have 5 pi turns. And then many different structures occur, and quite some of them are knotted and linked, or linked. So this one looks like a mess, but when you do a little in equilibrium, things are a little clearer, but then you do some mathematical tricks to understand this knot, and this comes a trefoil out of this. So that means this, but certainly from this you don't see too much yet. But here one can analyze a little more and understand what's behind. Now you see that many lines are just on surface outside, but some are running through the central area. And this, so in cross-section, here is one coming cross-section, while these are on surface. The one which goes through the volume, it has a very nice -1/2 profile, while the ones which are close to the surface are reasonably distorted, because it's close to the surface, while the cholesteric does not affect much. But what we see that they are twisting substantially. So if we go through the space, they twist substantially. So that means that this in our self-linking number, this twist part is certainly important part. Then that's something what comes immediately out of this. And then if you look on this, here I have just stressed this area. And then there are other examples. Here are this like Solomon ring, which you wouldn't recognize, but definitely with the little colors of different loops, and then simplifying, you get this. And Hofling, Whitehead link, and so even more complicated. So these things are reasonably easy addressable, and perhaps, but it's still a little work in progress. We must say that some stuff is still going on. Particularly, we can follow also the relaxation procedure, changing the chirality and then relax this. What happens? Where? What will first decay? Where? And so on. So then the energy is substantially depending on the disclination line reasonably well. For many of the many cases were all just on a very simple line when free energy depends on the disclination line. Not much depending on how many windings you have here. Now what is perhaps here an important question. Now, yeah, we can then put these topological questions because this procedure which was developed to trace the geometrical behavior can directly calculate our self-linking number for all these things which occur, and this number certainly comes, so you will see some are quite large, no? Like 1/3 is the self-linking number here, or even in this Hoff case, you have this self-linking number is 8. So, and all this, what means why it's high? Now, still it goes to our formula before. We have self-linking and linking numbers plus number of defects. This was equal to the charge. One would say, oh, what about charge? No, but we had this modular 2. And so that means this certainly, but if you calculate if they are even or odd, then you see that things work. So everything is consistent with what is allowed topologically. And then if you go to even higher n, so more winding, then you see that there is a kind of transition toward the surface. So that means all is expelled. So like expelling vortices from some magnetic in superconductors and so on. It's simply all defects concentrate on surface. They could be, this one is the lowest energy state, but this one is the less lower, but it's still, everything is on surface. So you have a thin layer where defects are concentrated inside nothing. It's just a simple cholesteric. Now, I'm not sure what the experiments will tell exactly, but some are still already going on, so I don't know. But here what is clear and interesting is that for this high chirality limit, this expulsion is observed very clearly, while in the very weak chirality limit, so that means when n was below 4, so it was practically no links, no knots, rather simple structures, and there was this range in between, then knots were observed. So it's a kind of balance when, so that means this is the area where disclination line can go through the central area. If it's just on surface, then things are different. But if it's through the bulk, then options are that the knots links can be formed. So that's coming out from such approximate hand-waving argument. So that means, I think, yeah, I must say that we have here tried to develop some of the topological description of, let's say, knotted and linked systems, particularly also working in cholesteric and in the nematic, but certainly this is not a very winded cholesteric, so we cannot talk a kind of smectic-like structures, except in this last case which I show. So all is with a rather modest winding. And then numerical experiments were also showing how we can demonstrate the knots inside and how they go together with the topological predictions. And then also the three-dimensional opal was a kind of excursus toward three-dimensional structures, how to make a topological ansatz, and then from that perhaps calculate the structure. Idea is that all this is not just playing with topology, but that we would somewhere use it. I'm not sure how many people are here which can help here with this.
Thank you very much. I was advised to use the microphone for questions. this question is this on?
The red light should be on.
Is totally off the wall. But
Yeah.
so if I look at your knotted structures, they can be distributed all across your sample in some way.
In this last example, yeah?
But then you can come in and do a local twist,
Yeah.
presumably break that.
Yeah.
So I wonder if you thought about whether or not this can give you something about distributed memory in the brain and things like that, where you have, that's right, it's off the wall, but
So you mean that that our brains are so much knotted as well?
Well, memory is distributed not in one place. It's all
Yeah,
over
yeah,
the
I
place.
understand,
So
yeah.
I'm just asking if you thought about
So
this
that
as a
means that one
possible-
can say, think about a field of transmission of the signals through your brain and how they connect or Okay, you shine the laser tweezer and then you break your connection somewhere.
I was curious if you had a chance to look at what happens with chi and tau director fields as you observe those structures, knotted defects, for example.
Do you mean the last one, which was knotted? Yeah, we didn't go yet in all detail analysis, but definitely one. But this, which I showed, were simply minus one half lines. So all the other ones, which are non-singular, then this is just dispersed. There are many of them around, no?
Yeah,
And
because
so,
there is also this analogy with biaxial nematics
yeah.
that Maurice was mentioning.
Yeah, that
and,
here also biaxiality could be traced. That's true. Simon has developed a kind of approach where one can trace it, but we must say we didn't do yet. Yes, thanks. Yeah.
Thank you. Any other questions? Oh, yes.
Just a short question in general. So my question, just a short question. You showed us a model for cholesterics, and nevertheless, between two plates, you had twisted nematics. Would you expect any difference if you take instead of twisted nematics?
Intrinsic or not intrinsic? Yeah.
Exactly.
Yeah, I don't know for sure how much was experiments. I know that some were done simply in twisted cell without a nemat, with the chiral, without chiral, but some were done with chiral agents. When the particular, I think 90-degree twist was usually without, while the more were using chiral agents. While energetically, it's true that this means if you have the chiral material intrinsic, then you will also see some kind of breaking of additional breaking of some states would be more preferred than the other. No? So that means definitely there are variations, but I'm not sure to what extent this was systematically studied on the experiments. But we can certainly trace the differences. But here, in this simple colloidal system, this twist, even in the simple nematic, was allowing that the disclination lines can be easy coming together in such a way that they can make coupling knots or whatever.
Thank you very much. I regret to say that